just finished the Your Turn activity, and so I just want to go through and just show you what the rough answers were for at least parts 1 and 2, so that you can check your work. And just a reminder, you should be showing your calculations as you go for these problems. So the function 1 over 1 minus x has these, the particular P4 that I've shown here. All of the coefficients for every power of x are just 1. And the derivatives, the kth derivative evaluated at x equals 0 is just k factorial. That's how we're arriving at the Taylor polynomials that you've calculated. So you can actually even guess now the formula for any degree Taylor polynomial of this function 1 over 1 minus x. Okay. And then cosine of x. Now this is sort of an interesting one because cosine is an even function, right? So when you're graphing cosine of x, right, and you did this in your in part 3, right, you notice that, right, if we have the best linear function is a constant function, and then our quadratic will be some function that kind of matches here, but cubic wise, the best cubic you found was actually the same as the parabola. It had a coefficient on the x cubed term of 0. So in particular here, what we're finding is that the best quartic polynomial had coefficients of 0 for the x cubed term and also the x term. And you can see that when you start considering the derivatives evaluated at 0, every other one, because we start out at the function evaluated at 0 is 1, that's just cosine. Derivative of cosine is negative sine, but sine at 0 is 0. And every other term is going to come back to sine. If you continue differentiating, you differentiate negative sine and you get negative cosine. So here we have a negative 1, then we differentiate negative cosine and we get back to sine, and so there's the 0 here. So every other time we differentiate, we have either plus or minus sine, and so we have a 0. And then the alternating ones, derivatives, are going to be either 1 or negative 1. So and that makes sense because cosine is an even function, and so we wouldn't be gaining anything by adding an odd power here because we would not be adding any accuracy, because on the left and the right different things would be happening, and cosine is even. So I'm not sure if that made a lot of sense. So if it didn't, don't worry about it too much. My point is, though, that we have an even function, and so it should be best approximated by even polynomials. And similarly with sine, we have an odd function, and so that's going to be best approximated with odd polynomials. And so here you saw your best fitting line was just x. Your best fitting constant is 0, and the best fitting parabola is still the line. So it's the parabola that has a 0 term in front of the x squared, so it's not actually a parabola. So you would end up with the best degree 4 polynomial is the same as the best degree 3 polynomial for a similar reason, as when we talked about cosine is an even function, sine is an odd function, so it's best approximated by odd polynomials. All right, so So let me just summarize then for you the general formula. So you've now gone through this process where you've computed degree 4 Taylor polynomials by computing derivatives of the function and then evaluating those derivatives at 0 and plugging in to our formula here. And so I just want to go through here and give you the general formula that you can use in this setting. And let me just look up here really quickly what so that I can give you the page in your book, or the reference in your book to where you can match up this formula here. So this is going to be essentially close to where it's right before example 8.5.1, but I'm going to go ahead and do this centered at x equals 0. So the degree n polynomial here, Pn of x, is just equal to f of 0 plus f prime of 0. Okay, and I'm going to go ahead and just make this a little more general than what's in your book, or not general, but just so you can see the pattern. F of 0 over 0 factorial, f prime of 0 over 1 factorial, f the second derivative evaluated at 0 over 2 factorial, and yeah, so this is, so the constant term is f of 0 over 0 factorial. The first term has coefficient f prime over 1 factorial. The next term has coefficient, the second derivative evaluated at 0 over 2 factorial, and so on. And the last term will be the nth derivative evaluated at 0 over n factorial times x to the n. Okay, so this is all when we say that we want the function and its first n derivatives to match our Taylor polynomial at 0. And we can play the same game if we want to match the function and its derivatives at some other point. So I'm going to go ahead and just write this formula down, and then we'll do an example. So Pn x centered at x equals a is just going to be f of a over 0 factorial plus f prime of a over 1 factorial. So the coefficients are going to look very similar, where we just plug in 0 instead of a. But instead of the terms writing this with powers of x, we're going to be using powers of x minus a. And so you'll see that what's happening then, so here's the second derivative at a over 2 factorial is our coefficient, and then we have x minus a squared. So you'll see that, and our last one will be f, the nth power, nth derivative at a over n factorial times x minus a to the n. And so you'll see that if we evaluate, so for example, notice that notice that P0 of x is equal to f of a. So P0 of a equals a, right? So the function values are equal. P1 of x is equal to, now when we do the differentiation, we need to use the chain rule, and so what we end up here with, okay, goodness, so let's see, so P1 of x, so when we differentiate, that first term goes away. The second term, what we're going to have is we differentiate x minus a, and so we have f prime of a over 1 factorial times the derivative of x minus a, which is just 1. Plus, and now we have to do this for every term, so then we're going to do the power rule with, so if I'm differentiating this term, we're going to use the power rule. So we'll end up with 2 times, and I'm going to go ahead and just put this constant term, right? This is just a number, right? So it's a constant number that I'm carrying along, and I'm doing the power rule on this power of x minus a. So x minus a squared, and then I'm reducing the power by 1, and then I multiply chain rule wise in here, but because the derivative of x minus a is just 1, that doesn't change anything. So, so notice here that this 2 is going to cancel with the 2 in the bottom. And then we have the next term was f, the third derivative. So I'll go ahead and up here write, I'll add another little term in here, x minus 3, x minus a cubed, right? So then if I take another derivative here, what you would see is 3 times the third derivative evaluated at a over 3 factorial x minus a squared. And then notice that this 3 is going to cancel, so this 3 here is going to cancel with the 3 in the 3 factorial. Okay, so then my last term, when I differentiate, is going to be n times fn evaluated at a over n factorial x minus a to the n minus 1. Okay, so I won't do all of these calculations out for you, but let's just notice that that this is now, notice that oh goodness. All right, so I'm sorry, I have a little typo here. This is not, so what I was trying to say here is that Pn of A is equal to A. So if I plug in A into this formula for Pn, all of the terms other than the first one become 0. Okay. If I differentiate Pn, that's what we were doing here, then notice that if I plug in into this derivative that we've calculated, if I plug in A, then I end up with the only term that survives is this first term here. Everything else goes to 0. Right? Because when I plug in A, then x minus a is 0, so we're just multiplying by 0 everywhere. So, so this is equal to f prime of A. And so you can kind of see already what's going to happen is that similar sort of cancellation is going to happen. So Pn, the kth derivative evaluated at A, is going to end up being equal to the kth derivative of f at A. So kind of reverse engineering that we end up having the function and all of its k derivatives match at A. The same thing would happen up here. We just did the calculation so often that I didn't, I don't think that going through it again with A equals 0 is as helpful. But I wanted you to see the chain rule and how the chain rule works with this polynomial. The other comment I just want to make is that, that even though this looks different from how you might write a degree n polynomial normally, right, if you imagine multiplying out like the x minus a here, so what I'm talking about, let me just direct your attention. Now I'm talking about this formula for the degree n Taylor polynomial centered at x equals a, if you imagine actually multiplying out all these powers of x minus a and then collecting all the terms, you would have a degree n polynomial, right? There would be an x to the n term, there would be an x to the n minus 1 term, and so on. Maybe the coefficients are 0, but you would have a polynomial of the correct degree when you multiply everything out here. So there's the general formula. Let's go ahead and use this general formula for an example. So example, let's compute the Taylor polynomial for e to the x centered at x equals 1. Okay, so now, again, what we are doing is we can just use this formula. So let's go ahead and say that the degree n Taylor polynomial is equal to, okay, and so f of 1 is equal to e. F prime of 1 is equal to e, and so on, right? Because f of x is e to the x, and f prime of x is e to the x, and so all possible derivatives are just e. So then what does that tell us? That says that the degree, so let's go ahead and just write out some of these. So P1 of x is just equal to e plus ex. P2 of x is equal to e plus ex squared plus e plus ex plus e over 2 factorial x. All right, so let's be careful here. We're centered at x equals 1, so we want for P1 of x e plus e times x minus 1. And then if we actually evaluate this a little bit more, right, this is the same. We don't have to resolve this too much, but we can just say this is e this is e plus ex minus e, right? And so this should just be ex is the best linear approximation near 1. P2 of x is going to be e plus e times x minus 1 plus, right, I'm just going to go ahead and separate this out a little here, plus, okay, and then I have e over 2 factorial times x minus 1 squared. Okay, so I can go ahead and just use the fact that this is ex plus e over 2 times x squared minus 2x plus 1. And when we work this out, so I'm just multiplying the e over 2 by all of these terms, and we have plus e over 2 here. So what we end up with then, let me go ahead and add one more page. Where am I? So we add one more page here, and we are left with this EX and this EX cancels, so we have x squared over 2 plus e over 2, and so on. Okay, so there is an example of the Taylor polynomial for e to the x centered at x equals 1. Let me just give you one more example here to consider. So let's see. All right. So I will have a your turn exercise, and I'll adjust your handout to include this your turn. So go ahead and compute the Taylor series, Taylor polynomial for sine of x centered at x equals, let's see, pi over 2. And go ahead and do that for the degree 4. So you can go ahead and just plug in. So what I did here is just P1 and P2. If I was to continue, we would have more terms. And so I'd like for you to try this for degree 4. Okay, so we'll stop here, and we'll pick up with the answers to this and a discussion.